Okay, I talked all big, but there really isn't that much more to this chapter. I think I was just scared. Okay, friction. Oh, but wait, no. I am going to talk more about friction. Did you know that friction is a thing? Okay, the big thing about friction is it always opposes motion or its tendency to move. So you can't ever solve a friction problem unless you know, like if something, I'm not going to even necessarily draw this on a flat surface. There we go. So if I know that something is either moving or impending motion is the word, you'll see something like that, impending motion, then friction goes the other way, just period, friction. Always has to go the opposite direction of impending motion. So when you see me work problems, and I think in chapter 6 is where there's just a whole bunch of problems to work, which is why I'm not working a whole bunch of problems now, you'll just see me draw this giant like impending motion arrow. Now, there's two types of friction, and this will probably be in chapter 6, but I just feel the need to get this out now. There's static friction, which is the friction that you get whenever something is not moving. Sorry, I'm watching my colleague run around. She's super cute. Static friction is when something is not moving, so that's the stuff that's preventing it from moving, and it's usually given, there's a coefficient of static friction, I can't spell, that is like a proportionality constant. That's so stupid. Why did I do that like grown-up talky thing? It just like, so if the normal force is 30, then this might be 0.3, and so the total frictional force is 9 newtons, or something like that. So it's like if something is sitting on here and it weighs 30 newtons and there's a 30 Newton reaction force, if the coefficient of static friction is 0.3 and it's trying to go this way, friction is fighting back at 9 newtons. That's a thing. Okay, that's a terrible example, but that's basically where we're going. And then there's the coefficient of kinetic friction, and kinetic means moving. So static is not moving. Kinetic means moving. And this one is mu sub k, and this is the coefficient of kinetic friction, and it's always smaller. You know, like whenever you push something, once you get it going, it's easier to keep it pushing. Does that make sense? Like, you know, you're pushing a box, and once you get the box moving, you can keep it going. So mu k is always smaller than mu s. So like once something is actually moving, but it's still the same thing. The force of friction is 30, say, times 0.2 or something like that. Something really important that I never understood with static friction as an undergrad, or just in general for a long time, is that this is actually the maximum resistance. So actually the picture I drew was terrible, because if you have a box sitting here, just like this, there's no friction at all, right? I mean, it's just not going, there's going to be no friction because it's not trying to go anywhere. The only time that you would get friction is if I started pulling on it. So basically the idea is, I think in my fake example, I said 9 newtons was the frictional force that it could do, would be like 9. So if I pull at 7, it'll only fight back at 7, which means it won't move. If I pull at 8, it'll fight back at 8. If I pull at 9, it will fight back at 9, and this is where it becomes, quote unquote, impending motion. So that's where it's like about to move, okay? But then once I pull it at 10, now it's moving, and the frictional force is no longer 9. It would be like that, sorry, not 0.6. It would be 6 newtons, like if I just pretended that that value was 0.2. So now it's only fighting me back at 6. So like I'm pulling at 7, it's resisting at 7. I pull at 8, it resists at 8. I pull at 9, it resists at 9. Then I pull at 10, and now it's moving and it's only resisting at 6. Okay, if that didn't make sense, maybe replay it because I don't have a better way to explain it. But so what I guess where I'm going with this is a lot of times students, whenever they draw friction problems, especially when things aren't moving, is they'll immediately draw the static friction as like the maximum. And you can't do that. You just have to be like this and then somewhere else be like F static has to be less than or equal to 9. And you just like put that off to the side and then you have to think about it later. Now, if it says motion is impending motion, then yes, it's at its max. It's about to move, everything. So this is a thing, and we'll get into it more. I just wanted to put this in your brain so it could start percolating, and then whenever we learn it for realsies, you'll be like, oh yeah, I remember we talked about this. Okay, friction. All right, spring forces. Did you know that when you pull on a spring, it expands? Yeah, okay. So basically the idea with a spring, so pretend this is just a flat table, and this is a spring, and it's here, and we're going to call this neutral. Okay, so this is the neutral position of the spring. So if I have a spring out to here, then the spring always wants to go back to your home. So I always think about Happy Gilmore when he's yelling at the ball that you want to go back to your home. Why don't you want to go back to your home? And then nobody else has seen this movie anymore, apparently. But now, so if I'm drawing a free body diagram of the box is the spring is trying to bring the box back home. So that's the direction of the force. Don't memorize this minus kx or plus kx. Stop it. Stop memorizing stuff. Look at the picture and see what's happening. Okay? If the spring is compressed, where's the spring trying to get? Back to home. This way. In this particular picture, this one happens to be in the negative direction, and this one happens to be in the positive direction. But, you know, I could just draw it here, and I could put neutral here, and now those beautiful equations that you memorized are all wrong because I switched the axes. So this is why you don't want to memorize equations. You want to understand what's physically happening, is because he's trying to get home. So now this one is positive and this one is negative. Make sense? Okay. So there's a spring constant, kind of like that coefficient of static friction. There's a spring constant that basically means the more you pull, the harder it wants to go back home. So there's this thing called the spring constant K, and it's usually measured in like newtons per meter, because the way that it works is the force of a spring is given by K times whatever, you know, this distance here turns out to be. So however far away it is, it's that. Okay? So if it's newtons per meter times meters, you get meters. I mean newtons. You get newtons, okay? So you have the spring force is kx. Don't worry about the stupid direction. Look at the picture and figure out which direction it's going, okay? And this is not what any other physics professor is going to say. They're going to say, but I always got it wrong that way. So if you want to do it that way, fine, read the book and do it the way the book is doing it. If you're always getting it wrong like I did, it's because you're trying not to learn anything, potentially, and it's just not coming. So however far away, and it doesn't, and I think what also got me is to be like, well, where's X? And it's like, well, in this paper, it's not X, it's Y, or whatever. However far away you are from neutral, the spring wants to get back from neutral, and it's either pulling to get back to neutral or it's pushing to get back to neutral. That's it. And what's crazy is eventually you might end up with a problem where you have like something like a collar on a slider, and it's like actually, you know, stretched so the collar is going this way while it's, and so you actually have a length change that is DDT and all this other kind of stuff. And if you're just memorizing, well, it's negative kx, then all that doesn't work anymore. You really need to understand the concept of how much is it off of neutral. And so this is a really big deal because it'll say stuff like the unstretched unstretched length of the spring. It might tell you the unstretched length of the spring, you know, maybe is 1 meter. And then be like, you know, this is 1 meter. And then in the picture, you might see that the spring is currently 1.5 meters. And then you can be like, oh, so it's stretched 0.5 meters. So this is the stretched or compressed amount. And again, the book is going to put pluses and minuses in it, and I'm going to warn you against that and just say what you really need to do is look at the picture and see what's physically going on and actually understand it. Okay, so it doesn't really matter how long the spring is or what's going on with the spring. You know, a 50-foot spring, if it's, you know, compressed or stretched 5 feet, is the same thing as a 2-inch spring that is stretched 5 feet if they have the same K value. So it doesn't really matter what the unstretched length of the spring is, except for like maybe the geometry of the problem. But really it's that K value, and they're going to give that to you. You have to find it experimentally. It just depends on how the spring is designed, like material and number of loopies and things like that. And then, of course, the longer you have a spring, the more it gets, you know, floppy and it doesn't work as well. So, yeah, just stop memorizing equations and actually understand what's going on. Real forces, inertial reference frames. I'm not going to worry too much about this, but just this whole section here is about that idea I know that I was been talking to you about before, where if you know you have, you know, an X position and a Y position and a Z position, the idea that if you are rotating, it's like if I'm watching a person, this is me, and I'm watching a person scuba dive and they're doing this, I can be like, I see what they're doing. But if a person is scuba diving and they're trying to watch me, I'm like going everywhere, okay? Because they have a rotating reference frame, but they don't know it. And that's why back in the day, whenever we thought that the Earth was the center of the universe and that Mars circled the Earth, the only way that Mars circles the Earth is if it does this. So it has to go forward and backwards. So like when they say Mars is in retrograde, the retrograde is when it was making these things, and these were called epicycles. You should Google it. It's really funny. So whenever your reference frame is wrong, that's how you end up with epicycles. We are not doing that in this class because that involves more work than we feel like doing. And this is like Physics 1. This is nothing. We've got this, okay? So it's just important that you know that it gets way more complicated, and that it all depends on your point of view, shockingly, okay? So if you know for sure that you are sitting still with respect to what you're looking at, it's clear. If you start getting stuff that's really, really weird, then you have to start questioning, wait, am I even sitting still compared to what I'm looking at? And then you realize that you are not, in fact, the center of the universe, and that you're going around the sun, and so is Mars. Okay? So that's how we learned astronomy. Yay! This is awesome.